The 2015 target air changes per hour was 5 air changes per hour. Now in 2021, it is 3 air changes per hour. So it's the entire volume of air in the house is leaking out 3 times every hour or less. You see it says ACH 50. So that means that that's basically using the blower door to depressurize the house to 50 pascals. So one thing the blower door does, it basically simulates a 20-mile-per-hour wind hitting the house. This is a blower door setup here. So basically it's a temporary door frame with a fan in it, and that measures the air leakage of the house. So the blower door is going to give you that cubic feet per minute number, the CFM number, and that, if you have that, you can calculate air changes per hour. Gauge here, our manometer. This will actually calculate if it's a super leaky 1850s farmhouse, if it can only get to like 30 pascals instead of 50, then the computer is going to extrapolate and say, well, best guess, I'd say this is what it probably would be if we could get it to negative 50 pascals. So we have to figure out what ring size that we need here based on what we get for the gauge reading. So here you can choose which of the ring size you want. So you have to make sure that the manometer is matching what you see here. So we go with ring A. And then this is your actual gauge here that's going to show you, if I was running this, it would show the pascals, the pressure, that negative 50 pascals, that's the standard that we're using. So we have to get the blower door pulling out enough air so that it can get to negative 50 pascals. And then at negative 50, the lower number here, the CFM, that's your blower door number. So when somebody says, what's the blower door number? It's the cubic feet per minute, the CFM number here. 50 pascals is the standard pressure. That's that 20-mile-per-hour wind hitting the house. So I set this and then I get it up to speed, and then I can read what the CFM is here. So this gauge, this is the newest RetroTech gauge. With this manometer here, you can actually input all of the information about the building. So the square footage, the volume of the space, the surface area, so the walls, the ceilings, the floors. So if you input all that information into the manometer, then it can automatically tell you what the air changes per hour is. Normally we're depressurizing, so we're pulling the air out of the house. That's how I typically will run a blower door test. Certainly for new construction, that's definitely how I'm going to run it. But if you are doing a blower door test in an older house, if you have vermiculite insulation that may have asbestos in it, if you have in an older house, you have steam pipe wrap that is asbestos, definitely don't do a blower door, because you don't want to make that airborne so that everybody's breathing that. I just did an audit yesterday where they had some mold in the house. So instead of pulling all of that mold into the living space from the basement, I turned the fan around and pressurized the house instead. So that's pushing all the air in. So any of the mold that's in the basement is getting pushed out. So it's not getting pulled into the living space. So you can use it 2 different ways, but typically we depressurize. Another reason you would pressurize is if you want to get real fun and creative with a blower door, you can pressurize. In new construction, you can use a theatrical fog machine on the inside of the house, and that's just filling the house with smoke. And then when you run the blower door, it's going to actually push that smoke through all of the air leaks in the house. So you can walk around the outside of the house and actually see where the air leakage is coming from. Definitely want to tell the fire department before you do that.
Those dampers
close
on a suction.
Correct. Yeah.
But they don't when you pressurize.
Right. So that's why when I do blower door testing for new construction, I always depressurize, because it's less accurate if you pressurize it. As far as the code enforcement officer is concerned, usually it's just the last thing that you do before you get the building occupancy permit. So right at the very, very end, which is really problematic because if I come in to do a test and I find that it's over 3 air changes per hour, now you've already sealed everything up. Now you've drywalled everything. You've kind of lost your chance to go in and fix things without having to tear things out. So pre-drywall is the best time, I think, to do a blower door test. It would be fantastic if builders had this kind of equipment to use during the building process and not just waiting until the end. How do you know if it's 3 air changes per hour or less if you have never had a test done before? So I heart codes. I love the building code because it is a great teaching tool.
We exchange the incoming air with basically a radiator over the outgoing air to exchange the conditioning of the air. Heat recovery ventilator is just the temperature. The ERV, the energy, is that exchange of humidity, is actually an energy exchange, and so it gets called an energy recovery ventilator. 99% of the time it's done through a ducted system, so there's one unit and then it runs with noodles throughout the building. You do want to use rigid ductwork most of the time. For the most part, it is true that you want hard ducts. Soft ducts create too much resistance in them. There are 2 different companies that make these cool little cylinders that go directly into the wall. They're really great for renovations when you can't get all those noodles run through the building. It has a core that you can kind of see there. Set them up in pairs. It spends 90 seconds with one sucking air in, the other one blowing air out. As it's blowing the air out, it heats up the core, and then 90 seconds later or something, they in sync switch directions, and so the air coming in is now passing over the core that just spent 60 seconds getting heated up, and the other one's blowing out. So they can actually get super efficient. Windows really make more of a difference than you kind of intuitively would think. They are a hole in the wall that's the lowest performance. They're always going to be significantly less performance than the wall is. They make a big difference to the comfort of the spaces because not only heat radiates, cold radiates as well. And then there's convection. So if you stand in front of anything really cold, just like the inverse of standing in front of a wood stove and you feel that heat radiating, it can be 70 degrees inside of a building, and if you stand in front of a high U value window and it's really cold surface, even though you're standing in 70 degrees, it's gonna actually actively suck heat off of you. So you're gonna feel cold even if you held a thermometer up and looked at the thermometer and told you were in a reasonable temperature. It's actively sucking heat off of you. And then the other thing that cold surfaces do is that cold air sinks. So the colder that window is, the air gets chilled on the window and then drops, and suddenly you're causing air movement and you're causing drafts. It may not even be a draft from inside to outside. A poorly performing window can actually cause a draft that's happening inside the building. And that is why traditionally we put heaters underneath the windows, is actually to stop that convection. This is the edge of one of these high performance windows. You can see that the bottom of it doesn't have any nailing flange. It just comes like this, and it's all thermally broken. So the image on the right is showing you with a heat difference, the right is the inside and the left is the cold outside, and how heat moves through the building because the glass performs better. So there's a significant benefit in the energy savings through the glass. There's the comfort. And once you put in those high performance windows, it makes it much easier to just go to heat pumps. It sort of transitions into different heating systems. You don't need so many, you don't need a heat pump head in every single room. When the exterior walls and the windows aren't losing a lot of heat through them, you can have one source in the building and go into a room that doesn't have that heat source, and it's not losing heat at such a rate that the whole entire building basically stays the same temperature. And then we have the ERV helping to move the conditioned air around the building. The need for heat source and conditioning in each room really has to do with the fact that you're losing so much energy, whether it's cooling or heating, through the wall that makes that room uncomfortable. And if we make the whole exterior envelope hold the conditioning more steadily, it doesn't have to be directed at every single space in the building. They actually will stay all comfortable with much fewer sources.